my class is on fundamentals of electrical engineering. We were on electrical machines after finishing circuits, and in machines itself we did two sections in DC machines, then two sections in transformers, and now we are on induction machines. We did one section earlier, and now this is the sixth section, and here we have three sessions again on induction machines. In this session, I'm discussing starters for induction motors. As was mentioned earlier, starters are essentially for induction motors. Why? Because there are two requirements. One is, of course, because everything is starting from rest, the machine is starting from rest, we need to have a good starting torque. Okay? But at the same time, so if that is the benefit that we want to accrue, at the same time, the cost, it should be at a low cost, and the cost is, of course, the current, because when everything is at rest, what happens is that large currents start to flow. So this has to be avoided. So it's always torque per ampere, which is going to be a good quality measure as far as starters are concerned. Okay? There are different types of starters, and we'll be discussing mostly problems that have already been there in the gate examinations. Okay? Like for instance, this for the first problem, where it's not a problem, it's a statement kind of question. Let's see. The following starting method for an induction motor is inferior in view of the poor starting torque per ampere of the line current drawn. So the quality measure is already given, and then several methods are given. Let's look at them one by one, such that we have a sort of a revision regarding the different methods. Direct on line starting is not very good. Okay, we have a huge starting current, normally 6 to 7 times the full load current flows. When the whole machine of the motor is plugged directly online with respect to the supply. Okay? So auto transfer method is a very good method of starting. In fact, it is before the soft starters, auto transformer method was mostly used for starting the transformers, starting the induction motors. Okay? Then we have series inductor method of starting. This is a very poor method. In fact, it's the poorest, because there is no additional gain with respect to the torque when compared to the current that is drawn by. As it is, there is an inductor, so this gives rise to perhaps more problems when compared to the other kind of starters. Okay? So the last of the lot, that is option D, is a good method. That is current method. Okay? So if you line them up according to the best method, auto transformer would be the best in the given options. Then would be the starter, and then you would have the direct on line starter, which is by itself poor. But the worst would be the series inductor method of starting. Okay, the power factor will also go down, okay, when we are having the series inductor method of starting. Okay. So moving on to the second question, which looks like a problem. An induction motor having full load torque of 60 Newton meter when delta connected. Okay, so delta connected means that the supply is completely available across the stator windings. Okay, each of the stator windings. Okay. There is a starting torque of 120 Newton meter. Okay, so the machine has just started, and at that time, by virtue of the quantities of the machine, it develops a starting torque of 120 Newton meter, wherein the starting torque is 3 times the full load torque. Okay, so this is the way that the problems can be understood. Okay, so quite a lot of starting torque is created. Okay, now what is the difference? Okay, so the same supply voltage, that is the same supply voltage is applied. If the motor is changed to star connection, so the same windings are now connected in star. So what happens is that the available voltage, though earlier when it was delta connected, was available completely across the stator winding, now it is not so. Okay, only 1/√3 times the same supply voltage is now being applied across each of the stator windings, because they are connected in star. Okay, the starting torque developed will be on. Okay, so here we realize that there are again a few relations, a few equations that we have better remember. One is, of course, that torque is now proportional to starting torque. Okay, but in what manner? X square times. What is X? X is the applied voltage. Okay, applied voltage, which gives rise to two quantities. One is the flux, and another is the current. So torque is always proportional to flux multiplied by current, and flux is created by the stator voltage being applied, and the current is also drawn from the supply voltage, and so we see that the voltage is actually proportional to the voltage is responsible for giving both the flux and the current. Okay, so if the current, if the voltage reduces to 1/3 times, then as is given in this particular problem, then we have connected the star windings in delta. Then what happens is that the starting torque reduces by 1/3 whole square. So we are having 1/3 multiplied by 120 or 40 Newton meter, which is option A from amongst the solutions given. Okay. So let's look at the third problem. So we just had a look at the fact that both the flux and the current matter with respect to torque. And so what happens is that there's another quantity also, which is what they come into. Okay. So we see that if the voltage goes down, okay, then both the flux as also the current is affected. So x square times the starting torque, the x square times the full load torque is going to be the starting torque. Okay. So let's move to the next one. A 3-phase squirrel cage induction motor has a starting current of 7 times the full load current. Okay. So this is the normal situation. That is the starting current is 7 times the full load current. Okay. And the full load slip of 5%. Okay. So SFL is also given. Okay. If the starting torque of 0.5 per unit is required, so what is per unit measured in terms of? It is measured in terms of full load torque. Okay. So the base is always going to be the full load torque, and so starting torque has to be 50% of it, which is what is given as 0.5 per unit. Okay. Then per unit starting current should be. So a new requirement has come up in the sense that we need to have the starting torque as equal to 50% of the full load torque. Okay. And we also know that we should also know that the starting torque is proportional to, as was mentioned earlier, both flux and current. So it is proportional to the starting current square. Okay. So both flux and the starting current are related with respect to each other. So it is the same as equal to proportional to IST square. At the same time, there is another aspect. If you look at the torque expression, I hope you remember that the torque is proportional to SR2 on the numerator and R2 square plus S square X2 square on the denominator. Okay? So what happens is that at the time of starting, or if you look at the torque slip characteristics, I hope you realize that at no load speeds, what happens is that the slip is very near to 0. So the normal working range is between 2% to 4%. Okay, at the most 6%. Okay, so that's the situation. But when you go to when the machine starts, the torque is proportional to 1/s. That's the reason why we are having hyperbolic kind of figure there. And in the linear zone, we normally operate the machine, and that is what is called as that's near to the no load speed, and then you also have the slip speed. Okay, so torque is proportional to not just IST square, that is starting torque, it's also proportional to 1/s. On the other hand, full load torque will be directly proportional to S, but starting torque will be inversely proportional to S. Okay? So this relation is also important. So two relations were talked about. Okay? So now we can come to an expression where T starting torque by T full load, which is what is asked, which is equal to 50% of 0.5, which is the same as equal to. Now we can substitute for IST by IFL whole square. Why? Because T starting torque is proportional to IST and full load torque is proportional to full load current. So IST by IFL whole square, and then inverse proportionality of slip can be given by T starting by TFL as equal to full load torque is equal to 0.5 is equal to IST by IFL whole square multiplied by SFL by 1, because the slip at starting is equal to 1. Okay, so now just simple substitution for all things will tell us that IST by IFL is the same as equal to square root of 10, because 0.5 divided by 0.05, where 5% is the slip, tells us that IST by IFL is equal to root 10. Okay, and that gives us the value of 3.16, and so C is the option. Okay, and so I hope this aspect has also driven in the fact that we have to look at starting torque with respect to full load torque. Okay, and what is given is 0.5, and at the same time the relation. Okay, of the current and as also the slip. Okay, so now let's go to the fourth problem. Okay, in each problem you learn or you revise something more. Okay, a 3-phase squirrel cage induction motor has a starting current of 7 times the full load current and full load slip of 5%. It's more, the first statement seems to be a repeat of everything. Okay, so the star delta starter. Now we are going to use a star delta starter because the current is 7 times. Okay, is used to start this induction motor. The per unit starting torque. It's not as though you have given that the starting torque should be 50%. Here we are asked what is going to be the starting torque. We use the same relation at the same time. So we use the same relation in what sense? T starting by T full load is equal to x square. Why? Because here the what we learned in the previous problem also makes its appearance, because the starter starter reduces the applied voltage. So we have x square. We also have I starting by I full load whole square from the earlier understanding, and we also have SFL by 1, where SFL refers to full load slip and 1 refers to starting. Okay. So here we see that we can replace IST by IFL as equal to 7. Okay. We also have the x square as equal to 1 by root 3 whole square. So 1 by root 3 whole square multiplied by 7 square multiplied by the slip 0.05 divided by 1 will tell us that the ratio of starting torque with respect to the full load torque as is asked is equal to 0.316. I hope this is clear. Okay. So we went through three. We had three relations. We put them together. Okay. So now let's go to the next one. 3-phase, 4-pole, 400 volt, 50 hertz, star connected induction motor has following circuit parameters. R1 is given as 1, R2 is given as 0.5, R2 is the rotor resistance referred to the primary, to the stator. Okay. And X1, X2 dash, which happen in both stator as also the rotor leakage reactances are 1.2 ohms each. Okay. And magnetizing reactance, which does not make a big appearance in this section, is equal to 35 ohms. Okay. So starting torque. So at starting, the shunt impedance is so large that it doesn't make any significance. Okay. So we will look at other things. The starting torque when the motor is started direct on line. So we don't have any X square coming in here. Okay, so use approximate equivalence equal. So what we have there, we know the relation for torque as equal to 3 into 60 divided by 2 pi ns, and ns needs to be calculated. It's a 4-pole 50 hertz machine, so it's 1500. Okay, and then we are having v square, so 400 square, not 400 square, 400 by root 2, because it's line, whatever is given is line to line voltage. So 400 by root 3 whole square, or 400 square by 3 multiplied by and the S is equal to 1 because starting torque is asked, and R2 is equal to 0.5. That is the point where the power is delivered. Okay, divided by 1.5, that is R1 plus R2 whole square plus X1 plus X2 whole square multiplied by S square, which is equal to 1. Okay, so just substituting everything, you get the answer as equal to A or 60. The option A or 63.6 Newton meter. Okay. Yeah, so this is just substitution. The only understanding happens to be that R2 will be referring to the output resistance. Okay. So let's go for the sixth problem. A 3-phase cage induction motor is started by direct on-line switching at the rated voltage. Okay. The starting current drawn is 6 times the full load current. Okay. So I starting by I full load is equal to 6. Okay. And the full load slip is 4%, so 0.04. Okay. The ratio of the starting developed torque to the full load torque. So PST by DFL is asked. Okay, there is no X square. Why? Because there is no voltage reduction methods being utilized. Voltage reduction methods that we talked about happen to be either the starter kind of starter method or the auto transform method. We have talked about the rest. Okay, there are other methods as well. Okay, so we have IST by IFL whole square, and then it has to be SFL by S star. The slip at starting is equal to 1. Just simple substitution for all values. 6 square multiplied by 0.04 tells us that the ratio is equal to 1.44. Okay, so that's the same expression we are using again and again. Okay? And then we come to the 7th problem. Okay, and this is the last slide. A 3-phase squirrel cage induction motor has a starting current of 7 times the old problem, and the full the 7 times the full load current, and full load slip of 5%, so 0.05. Okay? If as an auto transformer is used, so X square needs to come into the picture. Is used for reduced voltage starting to provide 1.5 per unit. Now we are given the torque, 1.5 per unit starting torque, the auto transformer ratio. Okay, so it's just the same problem used with different kinds of methods, not just different types of methods, but also different types of applications. Like for instance, in this case, we want to have a starting torque of 1.5 times when compared to the full load torque. So PST by TFX is equal to 1.5 multiplied by X square. Why? Because there is a voltage reduction technique involved in the auto transformer. So X square, that's going to be the auto transformer ratio. This X square multiplied by IST by IFL whole square multiplied by SFL by 1. Okay, so we can, in that case, we see that X square into 7 square, that is 49 multiplied by 0.5 is going to give us, it's going to be equal to 1.5. Okay? So simply we can, we see that x is equal to 30 by square root of 30 by 49, which is equal to 0.7835. So the turns ratio will be given in terms of the percentage as equal to 78.25. Okay? So we move to the last problem, which is a little different. Okay, so that's good. What do we have here? The speed of a 4-pole induction motor. So it is 50 Hz. That means it is 1500 RPM. Okay, by varying the supply frequency. Okay, so this is the new method. Okay, so we vary the supply frequency. Okay, while maintaining the ratio of supply voltage to supply frequency as constant. This is important. If ratio has to remain constant such that at higher speeds, where we near to the base speed, we have what is called as constant flux operation. Okay? So at rated frequency of 50 Hz and rated voltage of 400 volt, its speed is 1440 RPM. So what can we calculate? We can calculate this here, right? Because at 50 Hz, a 4-pole machine will have synchronous speed of 1500 and the rotor speed is given as 1440, which means that it has a slip is given by 1500 minus 1440 divided by 1500, all is equal to S is equal to 0.04. Okay, it's given there. NS at 50 Hz is equal to 0.04. Okay, so NS is 1500, so S is equal to 0.04. Okay, now we can also calculate NS at 30 Hz. Okay, because it is 120 F by 2, which is equal to 900 Hz. Okay, 900 RPM. Okay, so we need to find out S. But at the same time, we realize that the voltage at 30 Hz can be found out by because V by F ratio is maintained constant. Earlier it was 400 volt at 50 Hz, so we have V by F ratio is 8. So if we multiply 30 by 8, you get the new voltage, which is equal to 240. So voltage has changed, frequency has changed, and what is the torque relationship? We remember the torque relationship as 3 into 60 by 2 by ns, which we can say is equal to K, multiplied by S into E2 square by R, E2 square into R2, which we used recently, divided by R2 square plus S square X2 square. So now why are we using S here and not 1? Why? Because now the machine is running both at 50 Hz and 30 Hz and delivering full load. Okay, so we see that we now realize that now torque is proportional to not just V square, it's also proportional to S, and it's also and it's inversely proportional to F because of the V by F ratio that is there. Okay, so now I suppose this is clear. So V is for the S is from the numerator, V is for the flux V by F, and V is for the current. Okay, so everything is there, and so we just substitute. Okay, so for constant torque, we realize that 1 okay is equal to 400 square. Okay, that is the ratio that's equal to 400 square multiplied by the slip V square S by F, so multiplied by 0.04 divided by 50. Okay, so now we are saying constant torque means for both the situations, that is 50 Hz and 30 Hz, we see that torque is the same. So T 50 Hz by T 30 Hz is equal to 1, and so we have 400 square into 0.04 divided by 50 divided by 240 square multiplied by S and then divided by 30. So when you put them all together, S is the only quantity that we don't know. So S can be calculated as equal to 0.067. I hope this is clear. So in that case, you can calculate the speed as 9 into 1 minus SQ. So you get 840 RPM as the speed at which the rotor runs. Since both the voltage as also the frequency has come down, though we have maintained V by F ratio is constant. This is very, I suppose, the two main relations that we learned. Okay, and the fact that in this case it's proportional, the torque is proportional to S. Why? Because both at 50 Hz as also at 30 Hz, the machine is delivering full load torque. Okay, but of course, by maintaining V by F ratio constant, so voltage is reduced and frequency is also reduced. Okay, so the other relationship happens to be X square into IST divided by IFL whole square, that is PST divided by TFL. Okay, multiplied by SFL by 1 because S starting is equal to 1. Okay, so X square can be used whenever we have volume reduction techniques. Otherwise, it's the same. Okay, so this inverse proportionality there near to the starting times, but near to full load times, there is direct proportionality to S for torque. Okay, so these are the main important points, and with a simple understanding of these concepts, you will be able to do any problems in induction motor starters. And it's important because we have to start induction motor safely. Okay, so thank you.